Everybody. It's a great pleasure to have with us Dr. Karl Jansen. I think a lot of you know Karl very well. He's a long-time collaborator of us. He has also visited the Cyprus Institute many times. For those who don't know Karl, he has graduated from the University of Athens. He has been a fellow at CERN. Before moving to Tessie Zolliten, where he is currently the lead of the theory group. And I'm very happy to welcome him here because he has pioneered, as a lot of you know, large-scale simulations in Lattice 2CD, but he has also contributed in many other fields, like computational fluid dynamics, computational biology, and now quantum computing. So we are very happy to hear Karl.
Yeah, thanks a lot, Nina. It's really great to be here again. I really enjoy to be in Cyprus. It's a very rich country. It's a very rich island. At the moment, with happily all the rain you have, it's so green and blooming. It's really fantastic. So I wanted to motivate why we eventually need quantum simulations for models in high energy physics, and to come there and to show you one example. What I want to do, I want to bring you to quantum field theory, the basics of quantum field theory. Don't be afraid, it's really on a very basic level. And then I will show you the status, but also the difficulties of present-day lattice QCD calculations. Lattice QCD calculations that are done here at the Cyprus Institute to a very large extent. And then I will show you a possible solution of these difficulties that we have, which have to do with the origin of the universe, which have to do with the fact that there is more matter than antimatter and other questions. It is the matrix product states, and I will show you two examples of this. And finally, I will give you a glimpse at quantum computing that I have done myself for a particular problem. And I want to show you that quantum computing and quantum computers have become a reality today, but it's still in the infancy, and we cannot do much, but it is starting. Okay, in physics, there have been two revolutions. The first revolution is relativity theory, which says that if you measure time, it depends whether you are moving, with a certain velocity, or whether you are in a rest frame. And the formula for this is that you have the velocity you are moving with divided by the speed of light. And this relation here relates the time you would measure in this moving frame and in the rest frame. And this is not just a theoretical thing, this is something that you need for your daily GPS, because you minimally correct the clock of the satellite that is surrounding the Earth, and you have to correct for the time and therefore for the position. And it was found that this relation is really true. If you look at the lifetime of the muon is a particle which is very similar to the electron, but about 200 times heavier. Then in a particle collision already in 1977 at CERN, it was found if you accelerate the muons to 99.94% of the speed of light and put this velocity in here, then you find that according to this formula, the muon should live 30 times longer in the rest frame. And they could measure this and look at this precision here and the number they found. So this was the very first and very strong test of relativity, and it was shown that this formula is really true. And so we know that the speed of light is the maximum possible. This is another prediction of relativity. And we know from Einstein that the mass is actually the same as energy. Every mass basically is energy. And there was really a triumph in 2016, because then there was another prediction by Einstein who said if two very energetic objects in the universe collide, then it's possible that they curve space-time and that they actually emit some gravitational wave. This was a prediction from Einstein's theory, and for many decades people tried to find this effect. And it was only in 2016 that in such an experiment, where you have two arms, so there are lasers, here you have here's the laser, and you split the beam in one direction and the other, and if there is a gravitational wave, then it has the effect that it changes the length of one of these arms, and then you see some interference pattern. And in this experiment, this interference pattern was detected, it was interpreted as a neutron star merger so two neutron stars collided, they merged, and they emitted this purely gravitational waves. And this was then detected, and this is a spectacular test of general relativity. So nowadays, we really believe that this is the right theory of space-time. The second revolution was, of course, quantum mechanics. In quantum mechanics, you have some very strange behavior. If you would have a source, maybe you have marbles, and you have some obstacle with two holes, and now you throw the marbles against these holes, and what you would find, if you collect them here, you would find that they accumulate exactly at 2 points, and you have some density of these marbles at these points. When you do this with light, or imagine water, so you send light or water against an obstacle, and then it goes through these two slits here, then you know that you have this emergence of these waves here, they interfere, and what you have essentially is an interference pattern on the screen here, and you have maxima and minima, so you see accumulations at different points on the screen, so not two, but many of them. If you repeat the marble experiment with a quantum mechanical particle, for example, an electron, so you, so to speak, shoot an electron through such an obstacle, what you find is very remarkable. Instead of having the marble picture of just two accumulation points, you actually will find several maxima where these electrons accumulate and minima where there is nothing. So the picture you have here on the screen is actually the same as if you would have this light or this water waves. And this tells you that the quantum mechanical particle can actually act as a wave. If you have questions, please interrupt me if I can answer. Normally I can't, but try my best. And in the opposite, what was found, and also explained by Einstein, which was his Nobel Prize work, is that also light doesn't behave always as a wave. So it was found if you shot light to a certain solid state at a certain frequency, then this light behaves as if you would push out electrons from the solid. So light behaves as if it would be a solid particle that pushes out electrons from such a solid. So light can behave as a particle. And to summarize this, the quantum mechanical object, whatever this is, we cannot understand this, can appear either as a particle or as a wave, and this depends on the experimental setting. And this is the so-called particle-wave duality. So don't think of a quantum mechanical object as a particle or a wave. It's something else that only can appear either as a wave or a particle in real nature. And this strange word of this quantum mechanical particle is that energy can only change in discrete jumps. So we are used to, if we accelerate a car, we can accelerate the car continuously, so we have more and more energy continuously. If you would have a quantum mechanical car, it would jump from one velocity to the other. Particles can exist in different states simultaneously. We do not know in what state they are until we measure really in what state they were. And then the location and the momentum of the particles cannot be determined exactly at the same time. So I just wanted to illustrate that this world of quantum mechanical particles is very, very strange. And it's really outside of our daily experience. It's outside of our daily experience, but it's entering our daily life a lot. So quantum mechanics is based on laser technology. Laser technology uses quantum mechanical effects. If you think of transistors and therefore of your laptop and other electronic devices, it relies heavily on quantum mechanical effects. If you think of a tunnel microscope, where you really can detect very, very, very small objects, this relies on quantum mechanical effects. And there are future possible applications which are now pursued very much all over the world. This is quantum cryptography, that you make your bank account secure. And if this would develop within the next 10 years, and people succeed in developing this further enough, then all the bank accounts you can forget. They are insecure because they will immediately know what is your secret number. So this is something very, very serious that can change our life completely. There's quantum teleportation. So you can send signals basically immediately over very long distances. The Chinese have set up a satellite experiment. So there are 3 satellites in the orbit of the world, and they send information to one satellite, and the other satellite knows immediately what is the information on the other satellite. So this might also change completely how we transfer knowledge and information in our daily life in the future. And finally, there are quantum computers emerging from companies and also laboratories, and I will come back to this later. So why have I introduced quantum mechanics and relativity here for you? Because if we think of elementary particles, the most inner structure of nature, then they are described, let's put it this way, then they move essentially with the speed of light, and therefore you have to have relativistic effects, and they are quantum mechanical particles. So to describe the world of elementary particles, you need a relativistic quantum theory. You need a theory that combines relativity and quantum mechanics. And that's actually what we call quantum field theory, which is the theory that describes the interaction, the basic interaction of the most fundamental particles. And to repeat, don't try to imagine what these particles are, because they completely escape our daily life experience. We can only describe them mathematically, and we see the effects through certain experiments. Are there questions up to here? And how do we know that these particles exist? Well, we have large accelerator. Forget about this. I want to delete this. This refers to something else. And this is the Large Hadron Collider, which is actually built to find these elementary particles and to verify or falsify whether quantum field theories are really the concepts to describe elementary particle interaction. So that's a large accelerator based in Geneva. This is the Lake of Geneva here. It's underground, 175 meters below ground. So this is the accelerator. What you do here, you shoot protons and the antiparticles, the antiprotons against each other. Then you collide them in these interaction points here, and then you look what are the results of this collision, and what should come out of these collisions should be predicted by quantum field theories, if our quantum field theories are correct. And this can be measured in these detectors here. And this LHC has 4 detectors: Atlas, CMS, Alice, and LHC. That names. So this is the accelerator. This is another view. So this is Geneva here, and you see the circumference of this accelerator is 27 kilometers, so it's very large. It has injector rings which bring the proton and antiproton into this ring here. And what I want to point out here, so these are here again 4 detector stations, and these are collaborations, Atlas, CMS, Alice, and LHC. And a typical collaboration has about 3,000 members. So this means that this collaboration works with 3,000 members worldwide simultaneously, which is really a tremendous administrative and social problem. So they work on these events that come out of the detector in a certain way, and this works. So this is really a challenge. Just imagine your group here at the Cyprus Institute would have 3,000 members. I don't know. I hope it would be even lighter. And these are the detectors, and I just show this here to give you some imagination how big they are. Maybe you can see this, so there is a person standing here, and this is the size of the detector. So it would comprise the Cyprus Institute several times. This is Atlas and this is CMS, and you might imagine the size of the detectors. And this detector here is now empty. Once this is filled, it's filled with tons of electronics, millions of cables that will go to some computer center, and there the events that are measured in these detectors are analyzed. And with all this, we found really the most fundamental part. Now, to understand this particle interaction, there is really a lot of activity, in particular in Lattice QCD, which is pursued here at the Cyprus Institute a lot. In this approach, I just sketch it, I don't give you an introduction, we discretize space and time. We use a Euclidean matrix, and we use the Feynman path integral, which brings our standard model of particle interaction towards a statistical mechanical system. And there were lattice simulations of QCD, but also on the electroweak sector of the standard model in supersymmetry. And for all this, we use so-called Markov chain Monte Carlo methods. And this was really very important, but equally important is the development of supercomputers worldwide. I'll give you some examples. This is Summit. This is an IBM machine combined with NVIDIA GPUs. It's based in the United States at Oak Ridge National Laboratory. It has 2.4 million cores. 2.4 million cores that in principle can work together on a single problem. So we have 2.4 million of these laptops connected to each other and work on the same problem. And this machine can deliver already 200 petaflops. There's a race between different countries. I think at the moment the race is between the US and China. So China has at the top at the moment the Taiwan. Do I pronounce this correctly? Taiwan? Yes, thank you. We have guests from China, Chinese students who work together with Dina and me. So they can check me whether I'm saying the right thing here. And this is placed at the National Supercomputing Center in UC. It's hard language. And this field has 10 million cores. 10 million cores. And it delivers 125 petaflops. So we are really in an area of supercomputers where we are in a multi-hundred petaflop regime. And both in the US and in China, we are planning to have exaflop machines in the next years. So this is really a tremendous development that we see worldwide. To just give you a comparison to Europe, so I think the best machine at the moment is this date. This date stands for a certain mountain in Switzerland. This is a combination of Cray and NVIDIA, so again GPUs here. This is centered at the Swiss National Supercomputer Center, CSCS, in Switzerland. It has about 400,000 cores and 27 petaflops. So you see there is a certain gap between China and the US, but Europe is trying to fill this. Now I put the pictures, but the pictures are actually not very interesting. What you see is the supercomputers are all these cabinets here, and they are closed, so you don't see any cable. So it's rather boring, but these are the machines that deliver these performances. And with this setup, with this development in Lattice QCD, and using such machines or predecessors of those, we could make a lot of progress. So this is one of the real breakthroughs. So this is a Lattice QCD calculation of the low-lying variable spectrum, and this really comes from QCD alone. So there's only two inputs, which are these two particles here, and the rest of the spectrum comes out from QCD. So this was the very first ever confirmation that QCD really can generate the variable spectrum as we observe it in nature. And here in Cyprus, in the group of Dina, we repeated this calculation and also did it for different variables and found again agreement. And one could even go further, and to just give you one example, this a work again from the Cyprus group, which is really on the way to solve a very long-standing puzzle. There was some experimental finding by the European Union collaboration that very surprisingly, the spin of the quark, which is 1/2 measured, receives only very small contributions from the quarks inside the proton. So everybody was expecting that the quarks carry most of the spin of the proton, and the result of this experiment was it's very small. And this was called the puzzle because nobody understood this. And we made a very dedicated effort to disentangle the different contributions of the proton spin by first principle QCD simulation. And here you see the different contributions. So this is the proton spin of 1/2. And you see the contribution of the up, the down, the strange, the sum of those, and also the gluon. And what we actually could find that indeed the gluon carries a very large fraction of the spin of the proton, namely basically 30%. And this disentanglement here really solved this puzzle, because from this we learned that QCD really provides contribution to the proton spin from the gluons is a very large amount. So, we particle physicists, and particularly lattice persons, we are superheroes. We can answer any question for you. However, there are dangerous animals. I don't know how often I've shown this before. and these dangerous animals come with the fact that we use a certain method that I cannot explain to you in detail here, which comes under the name of this Markov chain Monte Carlo method. What you do in this Markov chain Monte Carlo method, you measure an observable, for example, the proton mass, by solving such integrals which are very high dimensional. So we have two of them in the numerator and the denominator. And what you need for this method is that these terms here, that they are real and positive, because you want to interpret them as a probability density. And if you can interpret this so-called measure as a probability density, then you can use this Markov chain Monte Carlo method, and you can compute the baryon spectrum, you can compute the spin of the proton, and many, many other quantities. However, if you have problems where this measure here, so this term here, is not real and positive, but complex, then Markov chain Monte Carlo method is completely fail. You cannot solve the integral anymore. And the reason is, if you have this to be complex, then you see very, very large oscillations and fluctuations of the integrand, and you would have to sample all these fluctuations which come with equal size here in order to get any reasonable value of this observable. And this is reflected here. So this is the error of a certain observable, it doesn't matter which one it is, as a function of the number of samples, as the number of integration points that you use to solve these integrals for a situation where this measure is not real and positive. And what you see are two things. So the error of this observable as a function of the number of integration points basically stays constant. Normally you would expect that this error decreases as a function of 1 over square root of the number of integration points, and here it essentially stays constant. And even more, if you compute the error of the error, which are these lines here, then you see that even the error is completely undetermined. So this means when you have problems where this measure here is not real and positive, you cannot get any significant results if you use Markov chain Monte Carlo with important sample. So now we could say this is bad, but we don't care, because we can compute the proton mass, we can compute the spin of the proton and other things. However, there are questions where this situation appears that we leave the situation of a positive measure. And this is, for example, the understanding of the phase diagram of our universe from the very beginning when the universe emerged. So this is here the phase diagram, so this is the temperature of the universe. So we live here in this corner here at the moment, so basically zero temperature. At the beginning of the universe, the temperature was very high, And this is the net baryon density, so this is the density of protons that you put, let's say, 1 cube centimeter. And the universe started at high temperature and at very high net baryon density. What we can do with our Markov chain Monte Carlo methods is to explore this line here very well. But as soon as we go inside, we hit the problem that we lose the positivity of the measure, and therefore we can only do simulations maybe very close to this line, but certainly not inside this phase diagram, which means that we do not understand the origin of the universe, where we had actually a core pure plasma, which means that we do not understand neutron stars, which have a very high proton density, which means that we do not really understand heavy ion collision experiments, and which means that we can also not test whether proposals of exotic phases like superconductivity really exist. So all this is not accessible to us when we use Markov chain Monte Carlo. And we also do chemical real-time simulations. This is inaccessible to this approach because we live in Euclidean time. And this means if you look at the heavy ion collision, then there are some suggestions what would happen. I will not go into this, but you see there are many different transition periods from a quark gluon plasma to the hadrons that we observe. And we cannot test whether such pictures are actually correct or whether this has to be modified. And when we shoot heavy ions together, whether this actually functions completely differently. And finally, we do not understand CP violation. So CP violation is charge and parity violation, which means if you look naively at the standard model and the equations that governs the particle interaction, and you would have an electron and you do a charge and a parity transformation, then naively the standard model would be invariant against this. However, in the electroweak sector there is an asymmetry, and if you break this asymmetry, then the particles and the antiparticles behave completely differently. And this can lead to an asymmetry between matter and antimatter. And this asymmetry, that there is more matter than antimatter, is actually the reason why we are here. If there would be an equal amount of matter and antimatter, they would constantly annihilate and they would not exist. So we better understand where this asymmetry comes from. So, and understanding this would lead to an understanding of our shear existence. Now, if you look at the electroweak and interaction of the standard model, you can actually estimate this amount of charge and parity violation. And what you estimate from this sector alone is that this asymmetry in some units is about 10 to the minus, it's vice versa. You can estimate this from theory that the amount is 10 to the minus 24. If you look at the measurements, what people find in experiments is that this asymmetry is actually 2 to the minus 10, which has a small factor of difference to the observed asymmetry, and this is much too small to explain the matter and matter. Now there is really a very exciting possibility that there could be a violation of charge and parity actually inducing the strong interaction of quarks. And this would lead to a term like this is not so important for you what it is, it's a so-called theta term. What is important is that this term here would lead again to a situation where we would lose the positivity of the measure. So to address this term here, it is extremely, extremely difficult, if not impossible, to do this with Markov chain Monte Carlo. So we better find something else. And the something else is that we change setup completely. And this setup completely is actually something that started, that is something where Lattice field theory started, namely to look at the Hamiltonian of the system. And in the Hamiltonian of the system, for example, for a spin-one half system, you have a wave function that is given by a set of basis states, And then it has a huge tensor with its indices I1 to In. This I1 to In labels the number of lattice points of states you have. And this tensor here is a coefficient matrix with 2 to the n matrix. And if you remember this, this nice example of the rice corn on the chessboard, if you start to put one rice corn here, 2 there, 4 there, 8 there, 16 there, 32, and so on and so on, and all of a sudden, so this is the television tower of Berlin, this is the Brandenburg Gate, so, but then very soon even Berlin will be covered by rice. And to solve such a system with, which has 2 to the n, the degrees of freedom, is essentially completely impossible. So therefore, even if in the very beginning of lattice field theory, the Hamiltonian was considered a lot, it was discovered that this approach through this tensor structure here actually becomes practically infeasible. And at the same time, Michael Kreutz in 1980 performed the first Markov chain Monte Carlo simulation that led today to the baryon spectrum that I showed you. And this was so successful that actually the Hamiltonian approach was completely forgotten. And it was put in a drawer, and it was said that if some clever guy comes and revives this, maybe then we can use this approach to solve the problems that I showed you in the previous slides. So now come 2-3 slides where this is really addressed to my friends from the Lattice to convince them that what I'm telling next is not nonsense. So you have 2-3 slides to check Sylvia and send Facebook messages and Twitter things that the Lattice person has to listen. And I wake you up when you should listen. So I told you this is the original problem. So this is the tensor, these are the basic states. And what I can do is I can write this tensor here as a product of 2 huge matrices. So I write this state here as a matrix with 2 indices alpha and beta. And the first index comprises all the indices from S1 to Sk, and the second Sk plus 1 until Sn. So these are this is a huge matrix, but I can rephrase this tensor in such a way, for example, by reshaping. Now what I can do here, I can, because this is a matrix, I can do singular value decomposition. So I apply some unitary matrices, U alpha alpha prime, and then I have the diagonal here as alpha prime as beta prime, and here I have B beta prime, B beta prime. And then I can do this for every side on my lattice. So on every side of my lattice, I make such a unitary transformation, and I define matrices now that have indices alpha j and alpha j prime, which can be huge. This can be really large indices. But in the middle, I have only diagonal matrices. And I can iterate this. So this is now an example for 3 sides. So I go to the first side, I do this singular value decomposition in this way here. Then I have my A1 here. Then I'm left with a smaller matrix C2. I do a singular value decomposition on this C2. So I get another matrix A2. And then I handle C3, singular value decomposition. This unitary matrices they cancel. And therefore I get now a product of matrices that are given by this A here. So I can write this state here as a product of matrices acting on this basis states. This is always possible. You can always do this by reshaping your tensor and writing this as a huge matrix to a singular value decomposition and write it as a product of the matrix. Mathematically identity. Question is it useful? Here is the answer. It can be useful if the effective size of these A's or these C's that are introduced through the singular value decomposition, if the effective size, mathematically, if the rank of this matrix is much smaller than the original matrix. And here I give you the singular values of such a matrix A. There are 2 examples. So this is the easy model in the transverse magnetic field, and this is the critical Heisenberg model. And what you see, there are only a few singular values that come in the order of 1, and there are many singular values that come at the level of 10 to the minus 12 or even smaller. And this is the case for both models. Also here you only have a few singular values that are rather large, and then many singular values that are very small. And therefore, in fact, in practice, you can neglect all these singular values. So I think we are very lucky, and actually we are not lucky, as I will show in the next slides. But it turns out, here experimentally, if we do this rewriting of this huge tensor C in terms of matrix product states, that all these matrices have a rank that is much smaller than the rank of the original matrix. And therefore I can neglect these singular values. So this means that I can use a particular ansatz. So I go from this huge tensor here to a so-called matrix product state. So these are its A's. And therefore we replace this complicated tensor by simple matrix products. These are really only matrix products. And this matrix I can choose as a D by D matrix, where I call this D the bond dimension. Okay. And this bond dimension is much smaller than the original size of the matrix that I got from the singular value. And therefore, to evaluate this here is an enormously reduced cost compared to the original formula. I think I skip this. And this leads to the fact that if I want to approximate the ground state with a certain accuracy or comes mathematics that I cannot prove. So these are mathematical statements that are proven in the literature. If I want to approximate the ground state with an accuracy epsilon 0 over L, then the minimal bond dimension that I need to reach this accuracy is larger than, so L is the number of sites that I have, is larger than L to the alpha divided by epsilon 0. And this means that these scales only polynomially with the system side and not exponentially as we had in the original model. And there's actually a theorem by Hastings that what I showed you, that the singular values are actually very small, that many singular values are very small. There's actually a mathematical theorem by Hastings who states that for a GAP system, there is an exponential fast convergence to the ground state. And this statement actually convinced me that this can be used for other applications, because from this statement I not only know that I find convergence, but I know that I find convergence exponentially fast. And therefore I have to control it, because I know how it converges, and fast converges to the solution. If I increase the bond dimension, meaning I increase the size of my matrices. You have questions after this point, because now I will come to some application of this.
Maybe one thing, I mean, you have very small eigenvalues, singular values, but they are meaningful.
Yeah.
So doesn't this disturb the system?
No, because of this theory here.
So
it basically shows that you always have this balance, that the density of these very small singular values does not spoil the statement. But what you say is correct. What is important is the gap system. If you would have a master system, then indeed it can happen that you have an accumulation of very small singular values, and therefore this theorem might not go through. Okay. So for the theorem, it's very important that the system is gapped. In practice, you know how mathematics goes. They give you upper bounds. These upper bounds have nothing to do with reality, and you can apply the method also for critical systems, and you find the same thing here. But you don't have this mathematical proof of it. Other questions?
The cost for doing this singular composition, do they still face the convergence?
No. This singular value decomposition was only for the purpose to show you that I can construct a matrix product state. So what you do now, you start with a matrix product state, which are matrices from the beginning that are of the size, let's say, 100 by 100.
And you need to construct them according to recreate your original.
That will come. Okay. Yep. So I can take this one.
Mathematically, it looks very similar to the cluster variation method in classical statistics. Are you familiar with cluster variation method?
No, I'm only familiar with DMRG, but cluster variation method.
It's used for phase diagram in material science, metallic system, and mineral science, and
okay, it can be very much related to this. I mean, it comes under a very
because there is a sort of factorization.
Yeah.
So with this sort of factorization, so they select size of the cluster, and then they consider that this cluster is distributed randomly with sort of corrections. The mathematics is the same everywhere.
Yeah, can I continue? So, you can ask in the discussion section. But thanks for this hint. This is really, I mean, this is rediscovered in many different areas now. So, the example is not QCD, but the Schwinger model. The Schwinger model is quantum electrodynamics in 1+1 dimension. It has a U1 gauge field coupled to fermion emitter. It shows very interesting phenomena similar as in QCD, the confinement of charges, bound states, higher symmetry breaking. Fortunately, the technical term for us lattice people is super renormalizable. So you can use the Bayer parameters. And it provides a very nice benchmark because it is exactly solvable in the master space. So therefore, it is very often used as a test bench for new methods. Okay, so this is the integral that I showed you. I integrate over the gauge fields and the matter fields, and this is my probability measure here. This is the gauge action, this is the fermion action. So the fermion action has this covariant derivative term, where you have normal derivative, and then the gauge potential here, and this gauge part is just the strength tensor. And if you would do this classically, you would obtain, if you do a variation on this, you would obtain the Maxwell equation. This now you can transform into a Hamiltonian, as you learned in this lecture. Right? So the Hamiltonian is given by conjugate momentum times the time derivative of the gauge potential minus the Lagrangian. And this conjugate momenta are the derivative of the Lagrangian with respect to the time derivative of the gauge potential, which is just the zero mu component of the heat strength. And then you can write down the Hamiltonian in this form here, so you rediscover the gauge invariant derivative here. You have the mass term, and you have the electric field square. So this E is the electric field, and the sigmas are the 2x2 Pauli resistance. And what this model has is we would call it gauge invariance, but in community I'm working with, they always call it Gauss law. So if you change the electric field, this has to be compensated by the charge that you go over. So if you have a charge, you have an electric field, and if you change the electric field, there has to be another charge to compensate for this. So this is the Gauss law. And then you can go through several steps, which I not go through here, and you end up essentially with this form of the Hamiltonian here, which is very nice because it has only Pauli matrices. So these are sigma x plus minus sigma y. So these are only really spin up and down operators. Then it has the mass term, it has a little bit of a complicated form, but what is important is that it has only Pauli matrices here. And then the electric field is expressed as a ladder operator. You can also try the electric field. And this x in front here is just, think of it as just being 1 over a squared, or against the lattice spacing. So if you want to take this Hamiltonian, and you want to take the continuum limit sending a to 0, this is equivalent to sending this x to infinity. And if you now use the Gauss law in this language, then what this is that a difference, if you increase the electric field by 1 by its ladder operators, then this has to be compensated by the charge. And the charge is expressed in this term here. And if you use this relation here, then you also can express this electric field operator here simply in terms of Pauli matrices. So you have a Hamilton operator that is simply expressible through Pauli matrices. And this is a perfect formulation for a Hamiltonian where we can apply this trick of these matrix product states. And this is also accessible for quantum simulators because you really only work with Pauli matrices. And this was actually done. There are 2 simulations now by this group here by Christine Muschig et al. And they have used this Hamiltonian and they put it on a quantum computer and simulated this Hamiltonian on the quantum computer, finding best results. But this was only recently. We started a long time ago. So how do you do this? Let's see. So what you want to do is you want to minimize the functional. So these are all possible states that you have, and you want to minimize this Lattice functional over all possible states over the Hamiltonian. So basically you want to minimize the energy and you express this in a certain graphical way. So what you do is you start with a certain matrix product state. So these are matrices of size d by d, let's say 100 by 100. And then you start by filling all matrices besides 1. Or you first fill all matrices, let's say with complex random numbers. Then you fix all matrices besides 1. So you fix all the matrices besides the one at lattice point A. Then you minimize the energy here only with respect to this matrix. Okay. Then, when you have done this, you fix this one, you go to the next A, and you minimize the energy with respect to that A, and then you sweep through the whole lattice back and forth until you find the difference in the energies of subsequent energies that fulfill certain criteria. Maybe for you, maybe it's more accessible in terms of an algorithm. So what I give you a Hamiltonian for a chain for lattices and sides. I give you a certain one dimension 100, and I give you a certain tolerance epsilon. Then I put some initial guess in all the matrices that I have. I compute through this matrix product states the energy of this initial guessed matrices, and I put the change in the energy to the 1. And then I say when my delta E is larger than epsilon and 1 is epsilon, I go to the first side for sweeping, and then I go and I sweep through the lattice. So I compute all the contractions, all the multiplications of the matrices besides the matrix AK at the point A. Then I solve an eigenvalue problem. H times this AK is the lowest eigenvalue times AK. Then I replace the matrix at the side K with the solution of the matrix I found here. So how I do this, I resheet this matrix in a vector, and then I have a standard minimization problem. And I change the energy at the side K with this minimal eigenvalue I found. And this I iterate, and then I test is the actual energy minus the iterated one divided by the actual energy smaller than this delta E. Is this smaller? So I put this into delta E, then I ask is this smaller than this epsilon, then I will stop. If not, I will iterate this. And that's basically the whole algorithm that I do.
Das ist konspirativ now.
No. The point is this procedure will exponentially fast converge to the energy of the ground state.
Yes, we need to get on principle. So, as I get not found in the ground state or
Maybe wait until the end.
And we can also discuss it privately. It's fine. And here is some example when in the Schwinger model we computed the ground state energy then we found the complete dispersion relation. We even came to the next state, and so we can really do this ground state and excited state properties. We get the excited states by simply projecting out the already found states. And this is now an example. So this is the one dimension. So this is the 1 over the size of the matrix, and this is the difference of the energy I found with the maximum one dimension I use and the actual energy at the given one dimension. And what you see here, I mean, note the scale. This is 6 times 10 to the minus 4, and you see I find a very, very rapid convergence to this ground state energy. This is the effect of this Hastings theorem that they converge exponentially fast to the ground state. Okay, now please close your eyes because I will make a big jump. Okay. So I told you what I want to use this for is for a problem where Markov chain Monte Carlo cannot work at all. And we were curious to find such a problem and see whether the so-called sign problem doesn't reappear in this dice. And for this, we looked again at this Schreiner model with 2 flavors, and we looked at the problem where we have a non-zero invariant density. And this is the phase diagram that can be computed in the master's case. So this is the particle number you have in the system, and this is the baryon density, so to speak. And what we found in this analytical calculation, which can be done for massless fermions, you find that at certain values of this chemical, it's called the chemical potential, you have a jump in the number of particles. So this is an analytical calculation that we have to reproduce in order to demonstrate that we can solve sign problems with this. And this is the anatomy, fine. And what we did, so we set out without detail. So this here is now from our matrix product state calculation, the number of particles. This is the baryon density, or the chemical potential. And what we found is indeed, as in the analytical calculation, at certain and the correct values of this chemical potential, we actually see this jump in the particle. Then there is a certain technique how to do this. And then we went, so we could reproduce this phase diagram, which means that with this method we don't have a sign problem, and we can go to non-zero baryon density. And we didn't see a problem at all in the calculation. And then we went to a case where we are not in the massless case, where we have an analytical solution, but we added a mass. And if you add a mass, there is no analytical solution available. And so we did the same calculation, we saw again these jumps, and then we could for the very first time and map out the phase diagram in the plane of the fermion mass and this chemical potential. And I'm not aware of any other method to get this phase diagram in this plane than with this matrix product states that I introduced. So this can really, if this would now work in higher dimensions, I can dream for a second, then I could really map out this phase diagram of BCD. So what are the prospects for going to higher dimensions? There are, so matrix product states can be represented in this language here. These are the matrices, they are multiplied together. These are physical indices, like the spin of the system. In 2 dimensions, you have such a network, and what you have to do is you have to contract such a network. So instead of matrices, you now have tensors, and you have to fill these tensors. You can go to exactly the same procedure, but the contraction, the multiplication of these tensors is much more complicated, and actually the computational cost scales with the 10th power of the 1 dimension. So even if you would have a 1 dimension of 10, where for the Schreiner model we didn't see any convergence, you would have a problem, a computational problem that scales with the 10th power, so this would be 10 to the 10. So we can forget about it. The state of the art here in solid states, condensed matter physics, they can do 16 by 16 systems, is very small. This is really the state of the art after 5 years of work to write such a test. So this means that we really need new ideas for tensor networks or in quantum simulations. Because quantum simulations don't care about the one dimension, they would take the system and they would solve it immediately. And here is a quantum computer. This is the IBM experience from IBM. What you have here are different levels. It's a very nice picture. You have different levels. You have cables that come from here and go down. The actual chip resides here. It's not very large. It has this size. And these different levels here correspond to different cooling stages. Because you want to have the chip here at, where's the temperature? At a temperature that is cooled down 118 times the temperature at interstellar space. This is really, we are talking about millikelvin. So it's really a tremendous endeavor to do this. The chip is shielded to 50 times less than the Earth's magnetic field. It's in a high vacuum and the pressure is 10 billion times lower than atmospheric pressure. And you do all this in order to not induce unwanted quantum transitions in the chip, in the quantum chip. This is why you do this enormous effort here. And then you do the computations here, and then you transfer the signal back to you. To give you, I spare you this informatics. So, maybe I can spare you this here. So, what we did with Tobias Hartung, a mathematician, a colleague of mine, we made some examples. So we performed a quantum computer calculation, and to have one practical example, we used the one-dimensional hydrogen atom, and we did this on a chip, the Agave chip of the company Betty, that is located in Berkeley in the United States. This is an 8-qubit machine, and we started this, so here you have the 8 qubits, this is how they are connected, and this is the actual chip, so you see the location of the qubits here. And we started by making first a simulation of the chip itself. And we found that if you want to solve this one-dimensional hydrogen atom, then we actually see very nicely an exponential convergence to the ground state property of this one-dimensional hydrogen atom. So if you would be interested in the ground state energy of a big molecule, chemistry, medicine, this would mean that you come to this result exponentially fast. So this was on the simulator, where we switched off the noise just to see how it works. Then we went on the real hardware. We used 1 qubit, this at a gate fidelity of 0.982, which means that 0.18% of all the times this quantum chip works wrong. There are wrong transitions and you get wrong results. There's also readout fidelity, which is 0.94, which means that in 6% in all the cases, you get a wrong result from reading out the field. So doing this, we still got the ground state energy of this one-dimensional hydrogen atom with a 5% error. So this is okay. But then when we went to 2 or 3 qubits, we couldn't get any significant result. And this is the big problem. Now there is a new generation of chips which are much better, and we are running other problems there, and it really looks better. But you can imagine that from this situation here, we have to go a long way to use quantum computers in practice. But if we would have these machines, we could solve the problems that I showed you before. Okay, so what I wanted to show you today is that Lattice QCD is a very much advanced notice. But I wanted to tell you that we have outstanding challenges, which is the chemical potential, so non-zero boundary density, CP violation, which means the explanation of the matter-antimatter asymmetry in the universe, and real-time processes. And what I wanted to show you that we have a new algorithmic ansatz, which are matrix product states and matrix product operators, which allow really to look into inner of a particle We had the test bench calculation of the 1 plus 1 dimensional Schwinger model. And what I could show you is that you can compute the spectrum there. So just imagine that this is UCD, this would be the viral spectrum of UCD is this approach. Once I showed you the example of chemical potential, it would not be done by marking. What I couldn't show you, which is really an interesting new game in town, you can look at entropy of 8 series, which is really interesting by itself. So all these things really overcome the sign problem. We didn't see any reappearance of the sign problem. The challenge is clearly higher dimensions. And here at the moment I put my cards on quantum simulations, as my cards are really the trump. Thank you for your attention.
So let's take some questions. It's open for questions. The tail will be and start. Okay. Anybody else?
Just it's a nice question. The states that you use to extract the ground state, I mean, they are not complete in that sense, right? So the base and upper bound could be energy or.
Yeah, but if you want, this is an upper bound that goes exponentially fast through the value.
So
if you
assume is
the bottom dimension, the size of the matrices. I mean, if I would reach the size of the matrix that corresponds to the number of indices that I had in the first place in the tensor, I would get the exact solution for this system. Right? So I will always come to the grounded solution that I want. The new element here is that I come there exponentially fast, so I can stop much earlier. And typically my one dimension is the order of 100, so I'm dealing with minimization problems of matrices of size 100. You can do this on the web.
Just for the quantum computing, so you said you went from 1 to 2 or more qubits, you didn't get significant results. That was because there's too much noise?
Yeah, I mean,
and then, so the question would be, how much is noise improved in the latest generation of chips? You mentioned you're doing some more experiments, and what do you foresee that we'll have, soon a generation of chips that will allow us to have a significant results? Or?
It's very difficult to say. It also depends on the problem. But you see, these fidelities, readout fidelities and gate fidelities, you have to multiply them.
Right.
So if you have such a fidelity and you have 10 qubits, your total fidelity is almost 0. So I think at the moment, I do not know really by heart, but I think this fidelity has 2 more 9s here, and this fidelity has another 9 here. Okay. So with this, we hope we can come to maybe 10 qubits, and that's the present situation. There are applications in the laboratory, so really this ultra-cold atoms, that people are performing experiments with 2000 qubits already. So these are Rydberg atoms, and they claim they can fully control this. And for certain problems, they have applied several hundreds of these qubits, and they got significant results. But this is something where you really understand your platform, your ultra-cold atoms platform extremely well. So you work on this for many years, and there you have already kinds of error correction. You can see when something goes wrong, and then you throw away this measure. For this commercial things, we get to the IBM, one qubit, and so on. This is not so far. But there is a huge community that looks at error corrections in quantum computers. We have to start somewhere.
Other questions?
So concerning this matrix product state approach, you mentioned that you can 2 plus 1 dimensions already work with. So people are working with.
Oh, definitely. No. This PEPS approach with this very wide scaling is something that has been shown that works in principle. It doesn't work in practice, but there are many different alternative approaches we go away from these PEPs and use something like a Gaussian ansatz. We actually we had one ansatz. We had a tensor network workshop recently in Zeuthen, and there was one presentation by Frank Verstraete. He actually computed three-dimensional systems. These were very particular systems, but he could do three-dimensional systems. These were some, I have to look it up, these were some very particular toy systems. But there is a lot of discussion and work going on to make this, not with PEPs, but with some alternatives to make this work in high dimensions.
Can we imagine algorithms that we can somehow correct those errors? Or is this completely non-thinkable that you would be able to correct for some of these biases or these errors that you get from the correlation?
So theoretically, there's a lot of work that in principle provide algorithms how you can correct. For example, just imagine you have a particular problem, and now you create a momentum state. And then you know that actually the result should be independent whether we have a momentum state that goes in this direction or in that direction. So you could halve your system, and you can do one calculation with the momentum in this direction and the other in this direction, and then you compare. And whenever you find that the difference is above a certain tolerance, then you throw away the measure. There's a very general theory how this momentum representation of the gates that you use in this calculation, you can do error correction. You can filter out the erroneous results. But this is something I'm thinking of at the moment to implement in practice, but it has to be tested, and you never know. But there are really several ideas how to use this.
Any more questions? Okay, so let's thank Karl again.